Imagine for a second that your computer isn't just a box of plastic and metal sitting on your desk, but a high-functioning, ultra-busy corporate office building. In this building, there is a boss who never sleeps, a filing clerk who can find any document in a nanosecond, a massive warehouse that stretches for miles, and a dedicated art department that paints 60 high-definition pictures every single second. This invisible world of silicon and electricity is what happens every time you click a mouse or tap a screen. But how does a collection of sand and copper actually think? How does it turn wall power into a video game or a spreadsheet? Today, we are tearing the side panel off the digital mystery. We are going deep into the motherboard and explaining every single computer component in detail. Let's start with the most important piece of silicon in the entire building, the CPU or Central Processing Unit. If the computer is an office, the CPU is the absolute boss. Ironically, the CPU is actually quite small, usually about the size of a large cracker. But inside that tiny square are billions of microscopic switches called transistors. The CPU's job is simple but exhausting. It executes instructions. Every single thing you do on a computer, from moving your cursor to firing a laser in a game, is broken down into a series of mathematical if-then statements. The CPU takes these instructions, does the math, and sends the results to the rest of the system. Modern CPUs are divided into cores. Think of these as individual workers within the boss's office. A quad-core CPU has 4 workers. An octa-core has 8. For a long time, the goal was just to make one worker run as fast as humanly possible, which we measured in gigahertz. But eventually, the workers got so fast they started to overheat. So engineers decided to add more workers instead. Some modern CPUs even have different types of workers, like performance cores for heavy lifting and efficiency cores for light tasks like checking for background updates. This prevents the boss from getting burned out on small stuff while a big project is running. But even the smartest boss in the world is useless if they have a terrible memory. This brings us to RAM, or Random Access Memory. In our office analogy, RAM is the top of the boss's desk. When you open a program, like a web browser or a game, the computer takes that data out of deep storage and places it on the desk so the CPU can reach it instantly. RAM is incredibly fast, thousands of times faster than your hard drive. However, it is volatile memory. This means the moment the power goes out, the desk is wiped clean. This is why if your computer crashes before you hit save, your work vanishes. The CPU can only see what is currently sitting on the desk of RAM. The more RAM you have, the bigger your desk is, which means you can have more programs open at the same time without the boss getting confused or having to clear off space. If RAM is the desk, then where does the data go when the computer is turned off? That would be your storage, which comes in 2 main flavors, the HDD and the SSD. Think of this as the massive warehouse in the basement of our office building. For decades, we used hard disk drives, or HDDs. These are mechanical devices with actual spinning platters and a tiny needle that reads data, much like a record player. They are great for storing massive amounts of data cheaply, but they are slow. Because the physical disk has to spin up to speed and the needle has to move to the right spot, there is a delay. Enter the SSD, or solid-state drive. This has no moving parts. It's all flash memory. In our warehouse analogy, an HDD is a clerk who has to ride a bicycle to the back of the building to find a box, while an SSD is a clerk who can just teleport the box to the front desk. SSDs have revolutionized computers more than almost any other component in the last decade. They make computers boot up in seconds and programs launch instantly. Within the world of SSDs, you also have NVMe drives, which plug directly into the fastest lanes of the motherboard, making the teleportation even faster. Now, all of these components, the boss, the desk, and the warehouse, need a way to communicate and a place to sit. This is the motherboard. If the CPU is the boss, the motherboard is the actual building itself. It provides the hallways, the elevators, and the electrical wiring that connects everything. The most important part of a motherboard is the chipset. This is the bit of silicon that acts like a middle manager, deciding which data goes to the CPU and which data goes to the USB ports or the audio jack. The motherboard also contains the bus lanes. Think of these as high-speed highways. For example, The PCIe lanes are the fastest roads in the building, usually reserved for the art department, which we'll get to in a second. Motherboards come in different sizes, like ATX, which is a full-sized skyscraper, or Mini ITX, which is like a compact studio apartment for small form-factor builds. The motherboard also holds the BIOS or UEFI, which is the very first piece of software that runs when you hit the power button. It's the building security that checks to make sure all the lights are working and the workers are present before it hands the keys over to the operating system. Let's talk about the art department, also known as the GPU or Graphics Processing Unit. While the CPU is a generalist who can do any kind of math, the GPU is a specialist. It is designed to do one thing and do it better than anyone else: calculate the color and position of pixels. If the CPU is a brilliant mathematician, the GPU is 1,000 artists working in a row, all painting one tiny section of a mural at the same time. GPUs are essential for modern gaming and video editing because rendering a 3D world requires millions of math calculations every second. The GPU has its own dedicated memory called VRAM, which is like a specialized mini desk just for textures and shapes. In recent years, GPUs have also become the primary power behind artificial intelligence. Because AI requires doing millions of simple calculations at once, the 1,000 artists of the GPU are actually better at it than the one brilliant boss of the CPU. This is why high-end graphics cards have become some of the most expensive and sought-after parts in the entire computer. But all of these high-performance workers generate a massive amount of heat. If you don't keep them cool, they will literally slow down to protect themselves from melting, a process called thermal throttling. This is where cooling comes in. There are two main ways to keep the building from catching fire: air cooling and liquid cooling. Air cooling uses metal heat sinks with fins to pull heat away from the chips, and then fans blow air through those fins to carry the heat out of the case. Liquid cooling is a bit more high-tech. It uses a water block on the CPU and a pump to move liquid through tubes to a radiator. It's essentially the same system your car uses to keep its engine cool. Liquid is much better at carrying heat than air is. So liquid cooling allows the CPU and GPU to work harder for longer periods without getting too hot. There is also the thermal paste, which is a gooey substance you put between the chip and the cooler. It might look like gray toothpaste, but it's vital because it fills in microscopic gaps between the metal surfaces, ensuring the best possible heat transfer. Without that tiny layer of paste, your high-end CPU would overheat in seconds. Of course, none of these components would work without electricity. This is where the PSU, or power supply unit, comes in. In our office analogy, the PSU is the power plant in the basement, but it's not just a plug. The electricity coming out of your wall is AC, or alternating current, which is high voltage and flows back and forth. Computer components are very delicate and need DC or direct current. The PSU takes that high voltage wall power and converts it into 12 volt, 5 volt, and 3.3 volt rails that the components can use. A good PSU is like a high-end surge protector. It filters the power to make sure it's clean and consistent. If the power fluctuates too much, it can end a delicate CPU. PSUs are rated by their wattage and their efficiency, like 80 plus gold or platinum. This tells you how much power is being wasted as heat during the conversion process. You never want to cheap out on a power supply, because if the power plant in the basement fails, it can take the whole building down with it. Now that we have the inner workings settled, we need a place to put them. That is the case, or the chassis. Many people think the case is just for looks, but it actually plays a huge role in performance. A good case is designed for airflow. It has specific spots for intake fans to pull cool air in and exhaust fans to push hot air out. If you put high-end parts in a case with no air vents, it's like trying to run an office with the windows boarded up and the AC broken. The case also determines how many hard drives you can fit, how big a graphics card you can buy, and how easy it is to manage your cables. Cable management isn't just about making the computer look pretty through the glass side panel. It's about making sure cables aren't blocking the airflow to the important parts. Let's look at the ways we talk to the computer, the peripherals. The keyboard and mouse are your input devices. Every time you press a key, a small electrical signal is sent through the USB controller to the motherboard, which tells the CPU what you've done. Mechanical keyboards are popular because they use individual physical switches for every key, providing better feedback and lasting much longer than the membrane keyboards found on most laptops. Then you have the monitor, which is your output device. This is where the GPU sends its final paintings. Monitors are defined by their resolution, how many pixels they have, and their refresh rate. A 60 Hz monitor redraws the image 60 times a second, while a 144 Hz or 240 Hz monitor redraws it much faster, making motion look incredibly smooth. This is vital for gamers because it reduces the time between when an action happens in the game and when you actually see it on the screen. We can't forget about networking. This is usually a small chip built into the motherboard or a separate PCIe card. It allows the computer to talk to the local router and the wider internet through an Ethernet cable or Wi-Fi. It's the mail room of the building, processing incoming and outgoing data packets and making sure they get to the right floor of the office. One specialized component that often gets overlooked is the sound card or DAC, which stands for Digital to Analog Converter. Computers think in digital ones and zeros, but speakers and headphones need analog electrical waves to push air and create sound. The DAC is the translator that turns the digital music file into the analog signal your ears can hear. While most motherboards have decent sound chips built in, audiophiles and music producers often use external DACs to get the cleanest sound possible without electrical noise from the other components. When you put all of this together, you have a system. But there is one more thing that makes it all work, and that is the drivers. These aren't physical parts, but they are the manuals that tell the operating system how to talk to the hardware. Without a driver, the Windows operating system might see a graphics card but have no idea how to send it instructions on how to paint a picture. This is why keeping your drivers updated is so important. It's like giving your workers the latest training and tools to do their jobs more efficiently. Let's talk briefly about the concept of bottlenecking. This is what happens when one part of the building is much slower than the rest. Imagine you have the fastest boss in the world, a high-end CPU, and the best art department, a massive GPU. But your desk, RAM, is only the size of a postage stamp. The boss will be sitting there doing nothing, waiting for space on the desk to open up before they can work. Or, if you have a great CPU and plenty of RAM, but you are still using an old, slow hard drive, the whole system will feel sluggish because the boss is waiting for the warehouse to send up the files they need. Building a great computer is all about balance, making sure every component is matched so that no one is stuck waiting on someone else. In the world of laptops, all of these components are still there, but they are shrunk down to incredible proportions. The CPU and GPU are often soldered directly to the motherboard, meaning you can't swap them out. The cooling system uses tiny heat pipes to snake around the cramped space, and the battery becomes a major player, acting as a portable PSU that has to carefully manage every milliwatt to keep the lights on for as long as possible. As we look toward the future, these components are starting to merge. We are seeing system-on-a-chip designs where the CPU, GPU, and RAM are all on a single piece of silicon. This is what Apple has done with their M-series chips and what smartphones have been doing for years. By putting the components closer together, data doesn't have to travel as far, which makes the whole system faster and more power efficient. It's like moving the warehouse, the desk, and the boss all into the same room. We are also seeing the rise of NPUs or neural processing units. These are new workers in the office specifically trained to handle AI tasks. While a GPU can do AI, an NPU is even more specialized, doing the same work while using way less electricity. In a few years, an NPU will likely be as standard as a sound card or a network chip. There is also the optical revolution on the horizon. Currently, all our data moves through copper wires as electricity, but electricity creates heat and resistance. Some companies are working on moving data with light, using silicon photonics. This would mean the hallways in our building would essentially be fiber optic cables, allowing data to move at the speed of light with almost zero heat. Every time you hit enter on your keyboard, take a second to realize the incredible journey that happens in a fraction of a second. A signal travels from your finger, through a driver, into the motherboard, where it's processed by the CPU, which pulls data from the RAM and the SSD, sends instructions to the GPU to update the screen, and pulls power from the PSU to keep it all going. It is a masterpiece of engineering, a tiny city of logic that we have built to extend our own minds. Understanding these components takes the magic out of the box, but it replaces it with something even better, an appreciation for the complexity of the modern world. When you know what each part does, you aren't just a user anymore. You are someone who understands the blueprints. You know how to fix it when it breaks, how to make it faster when it's slow, and how to build a better one when the time comes. The computer is the most versatile tool humanity has ever invented. It's a canvas for artists, a laboratory for scientists, and a gateway to the entire collective knowledge of our species for everyone else. And it all starts with those tiny transistors, those spinning disks, and those glowing lights. By mastering these components, we aren't just using a machine. We are harnessing the fundamental laws of physics to do our bidding. Whether you're building a monster gaming rig that can simulate entire universes, or just trying to understand why your laptop gets hot when you have too many tabs open, knowing the why behind the hardware changes the way you look at the digital world. It is a world of incredible precision, where a single mistake on a microscopic scale can stop the whole show. And yet, billions of these machines run every day, flawlessly, connecting us across the globe. So, the next time you hear your fan spin up or see your computer boot into its home screen, remember the workers in the office. The boss is at their desk, the warehouse is ready, the art department is painting, and the power is flowing. Your digital city is alive and well, ready for whatever task you give it next. Thank you for joining us on this tour of the Silicon Skyscraper. The hardware is always changing, getting faster, smaller, and smarter. But the fundamental logic of how it all works stays the same. Keep exploring the tech around you, keep asking what's under the hood, and we will see you in the next one as we continue to unlock the secrets of the machines that power our world.